So let's start this numerical question 4 from the first 2 units, and it's asked in the June 2015. The question says ABCD is a square of side 2 meter. So I'll take a reference square here. So A, B, C and D of side 2 meter. AB is equal to B, C is equal to CD is equal to DA. Charge of 5 nanocoulomb plus 10 nanocoulomb and minus 5 nanocoulomb are placed at the corners A, B, C respectively. Let us take them. So A 5 nanocoulomb, at B 10 nanocoulomb, at C we have minus 5 nanocoulomb. There is no charge at D, let it be as it is. So respectively, what is the work done in transferring a charge of 5 microcoulomb? So the charge we are carrying is 5 microcoulomb from D to the point of intersection of diagonals. Let's take the diagonals. There is 1 A to C, B to D. So I call the intersection of diagonals as O. So what we need to do here, calculate here, work done in carrying a charge. So I call the charge as Q naught of 5 microcoulomb from D to O. It's a direct formula, very simple one. That is, work done in carrying a charge will be equal to charge carried multiplied by the potential at final point minus the potential at initial point. So Q naught potential at final point, that is O, minus the potential at initial point is D. So first what we will do, individually find out the potential at final point and initial point, then we substitute the values, so we will calculate the work done. So first one, potential at initial point, I call it as VD. So the potential at this point, is due to the charges at A, B and C. The potential at D due to A is, I call it as VDA. Similarly, VBA and VDB, and I call this as VDC. So let's find out. The formula for potential is that 1 by 4 pi f0 charge by distance. So here 1 by 4 pi f0, that is K, will be taken common. So the remaining can be written as QA by DA plus QB divided by DB plus QC divided by DC. So K, let's substitute the values. 9 into 10 to the power 9. QA, that is charge at A, 5 nanocoulomb, that is 5 into 10 to the power minus 9, whole divided by DA. So that is distance between these two, that is 2 meters. 2 plus QB, 10 nanocoulomb, that is 10 into 10 to the power minus 9. But here the distance changes. That is BD, that is the diagonal. You can calculate considering the BDC as a right angle triangle at 2 meters. This is 2 meters. So BD square will be equal to 4 plus 4, 8, or BD will be equal to 2 root 2. We will get it as 2 root 2. The distance is 2 root 2. 8, we will get it as 8. The square root of 8 can be written as 2 root 2 plus QC, that is minus 5 nanocoulomb. In case of potential, if it is negative, the charge is negative, we have to take it as negative. So this is minus 5 into 10 to the power minus 9 whole divided by the distance is 2. So let's solve this. If you observe 5 into 10 to the power minus 9 by 2, here also we have minus 5 into 10 to the power minus 9 by 2, so they cancel out. Then I am left with 9 into 10, 90 by 2, 45, so I can write as 45, 90 divided by 2, 45, again I am left with root 2. So 10 to the power plus 9 and this is minus 9. So 10 to the power 0, that will be 1. So we get the value Vd. The potential at initial point as 45 divided by root 2 volts. So let's find out the potential at final point. So let me solve it here. And I will be going, that is, let me see, VO, again, the potential at final point will be due to charge at A, B and C. So I can write it as VOA plus VOB plus VOC. So I will be avoiding some steps to find out the final answer. The common point will be 9 into 10 to the power 9. QA 5 into 10 to the power minus 9 divided by half of the diagonal. You see OA, the distance from the final point O to the charge A, that is OA. Half of the diagonal, what we have diagonal as 2 root 2. So half of the 2 root 2 will be root 2. Plus 10 into 10 to the power minus 9 is also root 2, because VOB, that is QP divided by OB, O to B, half of the diagonal, this becomes minus, let us take one more step, 5 into 10 to the power minus 9 whole divided by root 2. So these two values, 5 into 10 to the power minus 9 by root 2 minus plus into minus 5 into 10 to the power minus 9 by root 2. You can cancel it. Then again 90, I will write it as 90 into 10 to the power 9 minus 9 by root 2. Simply this becomes 10 to the power 0, that is 1, 90 divided by root 2 volts. You can write it as simply capital V. So this is the potential at final point. So we got the potential at final point and potential at initial point. Let's place it in the formula, so we'll get the final answer. So I will continue, okay, right here. Q naught, the charge carried from one point to another, that is 5 microcoulomb, 5 into 10 to the power minus 6. Potential at final point, that is 90 divided by root 2 minus potential at initial point 45 divided by root 2. So root 2 can be taken common. 90 minus 45, again 45. So I get 5 into 45 into 10 to the power minus 6 divided by root 2. So let me solve. Approximately I get it as 159 point, I get the value, exactly I get the value as 1.59, 1, 2, 3 into 10 to the power minus 6. You can round it off. So work done, the unit of work done is joules, or you can also make use of Newton meter. So if we recall this, it's very simple. Calculating the work done, the charge carried multiplied by the potential at final point minus the potential at initial point. So if we are able to calculate these two values and we basically know what is potential, so the problem becomes very easy. So we can able to calculate the work done. Let's move on to the next question. Let's start with question number 5 from the first 2 units. This question is asked in March 2016. Let's start with this. When 2 capacitors are connected in series. So they are talking about 2 capacitors. Let's say C1 and C2. Connected in series and connected across 4 kilovolt line. So the 2 capacitors are connected across 4 kilovolt line. So potential is equal to 4 kilo, that is 10 to the power 3 volt line. The energy stored in the system. So the energy stored in the system of 2 capacitors connected in series is 8 joules. So you can call it as ES is equal to 8 joules. Full stop. The same capacitors, if connected in parallel, if the same capacitors connected in parallel across the same line, that is across the same voltage, the energy stored is 36 joules. So it is in parallel. I call it as EP, 36 joules. Full stop. Find the individual capacitances. Find the individual capacitances. That is nothing but C1 and C2. We have to find it out. You can make use of diagram for this one, or you can use it directly, calculate it. Energy stored. That's the formula for energy stored in series. So I have ES is equal to half capacitors in series and V square, and I can write as ES is equal to 1 by 2. When we have 2 capacitors in series, so the formula becomes C1 C2 divided by C1 plus C2 V square. So this is the formula when you have 2 capacitors in series. And the other is when we have capacitors in parallel, what happens? EP is equal to half CP V square. So this becomes 1 by 2 C1 plus C2 into V square. This is when 2 capacitors are connected in parallel. Let's substitute. We know the values of ES and EP. Let's find out. Let's substitute them and let's see what we will get. Let me go with this one only. EP 36 joules. So I write 36. When I take this one, 72 C1 plus C2, 4 into 10 to the power 3 whole square, that is 16 into 10 to the power 6. 4 into 10 to the power 3 whole square, 4 into 4 16, 10 to the power 3 if you square, 10 to the power 3 whole to the power 2, that is 10 to the power 6. So what can I write here is C1 plus C2 is equal to 72 divided by 16 into 10 to the power 6. 72 divided by 16 into 10 to the power 6. So if I solve it, I get 4.5. C1 plus C2, 72 by 16 is 4.5, and this 10 to the power 6 in the denominator shifts to numerator. It becomes 10 to the power minus 6. So this is one final equation. So you can call it as equation number 1. I have another formula, that is ES. I make use of this one. ES is 8 joules. So 8 into 2. Okay, let me take one more step. 8 1 by 2 C1 C2 C1 plus C2. I make use of this value in the place of C1 plus C2. That is 4.5 into 10 to the power minus 6. Again this is 16 into 10 to the power 6. Okay. So what happens? 16 8 into 2 C1 C2 divided by 4.5 into 10 to the power minus 6, 16 into 10 to the power 6. So this 16 and 16 gets cancels. When I take the values on the other side, so I can write it as, you see, if I take this one to denominator, minus 6, so minus 6 minus 12, I get C1 C2 is equal to 4.5 into 10 to the power minus 12. So I get the value C1, C2, taking the values onto the LHS side, 4.5 into 10 to the power minus 12. Let's call this as equation number 2. So if I take the data what they have given, making use of that one as at a point, I am starting down with the values C1 plus C2, C1 and C2. So I should make use of these two equations to find out C1 and C2. For this, I am making use of a formula C1 minus C2 whole square is equal to C1 plus C2 whole square minus 4C1 C2. An algebraic equation, that is A minus B whole square is equal to A plus B whole square minus 4AB. So let's substitute the values here, because we have C1 plus C2 and also we have C1 C2. So if I substitute those values, I get C1 minus C2. C1 minus C2 will be C1 plus C2 will be there. Adding up equation, I can find out the individual values. So let's proceed. C1 minus C2 whole square. C1 plus C2 is 4.5 into 10 to the power minus 6 whole square minus 4 into 4.5 into 10 to the power minus 12. That's all this. 4.5 so 20.25 into 10 to the power minus 12 minus 18 into 10 to the power minus 12. So 10 to the power minus 12 can be taken common. So 20.25 minus 18 will be 2.25 into 10 to the power minus 12. This is C1 minus C2 whole square. I write C1 minus C2 taking square root of both sides. Square root of 2.25. I get it as 1.5 into 10 to the power. Taking square root for this 10 to the power minus 12, you can take it as 10 to the power minus 12. Square root means to the power 1 by 2. So minus 12 by 2 is 6. So this becomes 10 to the power minus 6. So I call this equation as 3. C1 plus C2 is there. C1 minus C2 is there. So now I add equation 1. This I write C1 plus C2 is equal to 4.5 into 10 to the power minus 6. When I add these two gets cancelled out, I get 2 C1 6 into 10 to the power minus 6. They will be taken common when we are adding. So I get C1 is equal to 3 into 10 to the power minus 6 farad. So I got C1, C2 will be equal to 4.5 minus 3. So you can easily find it out. So 1.5 into 10 to the power minus 6 farad. So this is the solution for this question.